In this video, we are going to learn how to find the surface area of a parameterized surface. In the previous video, we learned how to parameterize a surface in terms of two parameters, and now we're going to find the area of that surface over some restricted domain. So the area of a smooth surface S parameterized by R of uv, where S is covered just once as u and v range throughout the parametric domain D, is defined as A of S, which is the area of S, the surface, which is equal to the double integral over the surface S of 1 ds, which is equal to the double integral over the domain D of the magnitude of the cross product of the partial of R with respect to u crossed with the partial of R with respect to v, and then integrating over the area defined by that domain. So this is how we're going to compute surface area. We're going to take the parameterization, find the two tangent vectors by taking the partial with respect to u, partial with respect to v, take their cross product, find that magnitude, and then we're integrating that magnitude over the area defined by the domain D. So just to highlight this whole piece here, that is our surface area element that we're integrating over. Which now, as far as notation goes, we do have new notation with this ds. That indicates that we're integrating over a surface. If you think back to line integration, we had a lowercase s when we were integrating with respect to arc length, and that was equal to the single integral of the magnitude of r prime of t dt, which put a magnitude in place of the ds. So here, when we have a capital S, that indicates that we're integrating over a surface. So we'll see this more and more as we move into our surface integrals. So now, why does this work? Well, just briefly, over an infinitesimally small region of a surface S, the area of the tangent plane will closely approximate the area of the surface. Right? So if we're in a really small region, basically the tangent plane and the surface are indistinguishable. So we can partition the domain into infinitesimally small regions and compute the area of the tangent plane over each of these regions. And when we start summing up, that's where integration comes into play. And the area of the tangent plane can be found by computing the area of the parallelogram formed by the tangent vectors to the grid lines, which is the partial of r with respect to u and the partial of r with respect to v. So essentially, going all the way back to the first unit of this course, that magnitude of a cross product is nothing more than the area of a parallelogram. Another way to think about this definition is this magnitude of the cross product is a scale factor that makes the area of the region D equal to the area of the surface that we're integrating over. Right? So this is why it works. It's based on those tangent planes that we were finding in the previous video. So that's why we do those exercises to find the cross product, because we're going to continue to use that computation now for our surface area integrals. Okay, so let's start with a parameterized surface. So set up an integral to find the area of the helicoid parameterized by r of uv, which is u cosine v, u sine v, 3v, over the region defined by u bound from 0 to 1 and v bound from 0 to pi. Okay, so first thing we need are those two tangent vectors. So we're going to find the partial of r with respect to u. So that's going to be cosine v, sine v, 0. Then we're going to find the partial with respect to v. So negative u sine v, u cosine v, and 3. Now we need to take the cross product of these two vectors. So crossing those two vectors, we set up our matrix to find the determinant. So we put both vectors in, so cos v sine v 0, negative u sine v, u cosine v 3. So we get 3 sine v, negative 3 cosine v, and then u cos squared plus u sine squared is just going to be u. So that's the cross product vector. Then we need to find the magnitude of the cross product vector. So that's going to be the square root of 9 sine squared v plus 9 cosine squared v plus u squared, which is equal to square root of 9 plus u squared. So setting up our double integral for the surface area, so we're taking the double integral of the square root of 9 plus u squared du dv, where u goes from 0 to 1 and v goes from 0 to pi. Okay. Now we're just setting up this integral. We're not going to evaluate. And actually evaluating this integral would be a little bit of a challenge. It would require trig substitution. You would have to let u be equal to 3 tangent theta and go through the process of a trig substitution integral. Or you can look up a table of integrals and see what that would be equivalent to. But for right now, really just going through the process of setting up this integral by finding the two tangent vectors, their cross product, their magnitude, and then we stop here. Let's look at a few examples where we know the surface area and we can confirm it with this double integral. So find the area of the part of the cylinder x squared plus y squared equals 25 between the planes z equals -1 and z equals 3. Now, we don't need to sketch it, but it's always nice to just have a visualization of what we are looking at. So essentially we have a cylinder around the z-axis. It's going to go below the xy plane. Right, so that's z equals -1, z equals 3. So we're finding the area of the cylinder, which if you think back to geometry, we often call this the lateral area, right? It's the side of the cylinder. So thinking back to geometry, right, the radius of this circle is 5. So it would be the circumference times the height for that surface area. So 2 pi r, so 10 pi. Height is 4. So we should get 40 pi when we go through the calculus approach for finding the surface area. So let's go through that process. First thing we need to do is parameterize the cylinder. So because the cylinder has only two variables, we parameterize it like a curve with one variable. That leaves the other variable for z. So I'm going to use theta and z as the parameters then. So then the x component would be 5 cosine theta. Y component would be 5 sine theta. Right? Remember, on the cylinder, the radius is constant. And then z. And as far as our domain restriction goes, theta is bound from 0 to 2 pi, and z is bound from -1 to 3. So now we need to find the cross product of those two tangent vectors so that we kind of work in a more efficient manner. Let's just set up the cross product and take the partial derivatives as we set up this cross product matrix. So the partial of r with respect to theta, that's going to be -5 sine theta, 5 cosine theta, 0. And then the partial of r with respect to z is going to be 0, 0, 1. So that's going to make for a nice computation here. So we get 5 cosine theta. Then we get the negation of -5, so +5 sine theta. And then we get 0 as our cross product vector. And then the magnitude of that is going to be the square root of 25 cosine squared theta plus 25 sine squared theta, which is equal to 5. Okay, so that means we are setting up the double integral of 5 d theta dz. Theta goes from 0 to 2 pi. Z goes from -1 to 3. This is separable, so we could say 5 times the integral from -1 to 3 of 1 dz times the integral from 0 to 2 pi d theta. So that's going to be 5 times z evaluated from -1 to 3, theta evaluated from 0 to 2 pi, which is going to be equal to 5. And then 3 minus negative 1 is 4. And then 2 pi. So 20 times 2 pi is 40 pi. So that's a good sign. We confirm the surface area that we expected to get by using the geometry formula, now with our calculus approach and a surface integral. So let's do another example where we know the answer. So find the surface area of the sphere x squared plus y squared plus z squared equals 4. So surface area is 4 pi r squared. R is 2, so 4 times 4, so we should expect to get an answer of 16 pi. Now let's go through the process of doing this parametrically. So first thing we need to do is define the sphere. So we'll go theta and phi. Think spherical coordinates here. Radius is fixed, so we go 2 sine phi cos theta, 2 sine phi sine theta, and 2 cosine phi. Our bounds, theta goes from 0 to 2 pi, and phi goes from 0 to pi. Remember that restriction when we were working in the spherical coordinate system. Now, we're going to skip the actual cross product and go straight to the magnitude. And this is going to be a helpful fact to save us a little bit of work here. Of course, we can compute it and get it out, but the magnitude of this cross product of the tangent vectors is going to be 4 sine phi. And this actually comes from our work in the spherical coordinate system. This is nothing more than just rho squared sine phi. So if we decide to parameterize a sphere using spherical coordinates, then the magnitude of the cross product of the tangent vectors is going to be rho squared sine phi. So that can save us quite a bit of work. So then we're going to get the double integral of 4 sine phi d theta d phi. Theta goes from 0 to 2 pi. Phi goes from 0 to pi. Again, we have a separable integral. So 4 times the integral from 0 to pi of sine phi d phi times the integral from 0 to 2 pi of 1 d theta. So this is 4 times negative cosine phi from 0 to pi times 2 pi. So 4 times cosine pi is negative 1, so negating that, that'd be 1, and then minus negative 1 is plus 1, so times 2 pi, which is, as we expected, 16 pi. Now, since we can find that surface area with a formula, and the same thing in the previous example, these don't really give us any advantage. If anything, they're more difficult for us to compute. But we're often not going to be finding the surface area of the whole sphere. There's typically going to be a restriction, and we're going to be just looking for part of the surface area. So how would the integral change if we only wanted the area of the part of the sphere x squared plus y squared plus z squared equals 4 above the plane z equals 1? So now we only want a little portion of the surface area. So z equals 1. If we take the z component of our parameterization, that means that 1 equals 2 cosine phi. So 1/2 equals cosine phi. And that means phi equals pi over 3. So how would we change the integral? Well, we're going to change the bound on phi. So we're still taking the double integral of 4 sine phi d theta d phi. Right? The magnitude of that cross product doesn't change. But now theta goes from 0 to 2 pi, and phi goes from 0 to pi over 3. Right? So just to highlight, that upper bound of integration is changing. And that will give us the area of just this portion above z equals 1. Now, what if we have a surface defined explicitly where we would use a trivial parameterization? Is there a way to make the computation a little bit more efficient? So let's parameterize using a trivial parameterization. So r of xy means we have x, y, f of xy. Right, so we're working through the case where it's a z equals in terms of x and y, for our trivial parameterization, but we can adapt this if it was x equals or y equals as well. Okay, so we're going to find the cross product of the two tangent vectors. So we'll do that right in the matrix. So I, j, and k. So the partial with respect to x is 1, 0, partial of the function with respect to x. And then with respect to y, it's 0, 1, partial with respect to y. So our cross product vector is 0 minus f of x, so negative partial with respect to x, and then partial y minus 0, so the negation of the partial with respect to y, and then 1 minus 0 is 1. So then the magnitude of that cross product vector is equal to the square root of the negation of the partial with respect to x squared, the negation with the partial with respect to y squared, plus 1 squared. So we are setting up an integral, so that's going to mean the double integral over whatever region D is defined, square root of 1 plus partial with respect to x squared, right? The negative can be eliminated for both these terms, partial with respect to y squared, dA. And I just changed the order so that it matches more typically what is given as a formula. So if we are given a surface explicitly, we can jump right into our double integral by finding the two partial derivatives and squaring them. So it saves us some time. That being said, if we forgot this, then just go through the process. Create a trivial parameterization of whatever surface you're working with. Find your two tangent vectors, cross them, magnitude, setup. So we don't need this. We definitely can stick with the parameterization route. And if for you, having one method makes more sense, then stick with the parameterization method, because those previous examples we could not do this way. But the examples that are going to follow, we're going to try to use this approach. So find the area of the part of the plane x plus y plus z equals 2 in the first octant. Okay, so just to have a visualization of what we're defining. So we have the triangular piece of the plane. All the intercepts are 2. So we're finding the area of that part of the plane right there. So we can solve this explicitly. So we could say z equals 2 minus x minus y. Right? So we have an explicitly defined surface. So instead of using the function notation, I'll just use the partial notation. So partial of z with respect to x, that's negative 1. Partial of z with respect to y, that's also negative 1. So we're going to set up the double integral over the region D of the square root of 1 plus negative 1 squared plus negative 1 squared dA. So that means we have square root of 3 times the double integral of d over d of 1 dA. Well, here we can actually avoid integrating because this is just area. So if we can find the area of the region that we're supposed to be integrating over, well, then we can just multiply by square root of 3. So since we used a trivial parameterization, we're integrating over a region on the xy plane, which is defined by those intercepts at 2. So this is the domain D that we're integrating over. Right? If we wanted to, this would be y equals 2 minus x. We could set up our bounds of integration, but this is a triangle. We know how to find the area of that triangle. So that's going to be square root of 3 times the area of that triangle, which is 1/2 base height, so 1/2 times 2, which is just 2. So we get 2 square root of 3. So definitely more efficient when we have an explicitly defined surface to go through this approach. Let's look at another example. Find the area of the part of the paraboloid z equals 4 minus x squared minus y squared above the xy plane. So again, just to visualize what we're dealing with, so we have a paraboloid that opens down here, and the radius of that circle is going to be 2 when z equals 0. So we can find the partials. So partial of z with respect to x, that's going to be negative 2x. partial of z with respect to y, that's going to be negative 2y. And we can jump right into our double integral, square root of 1 plus negative 2x squared plus negative 2y squared dA over the region D. So that's going to be the double integral over the region D of the square root of 1 plus 4x squared plus 4y squared dA. Now the region that we're integrating over, because we're doing the trivial parameterization, would be that region in the xy plane. That's going to be a circle of radius 2. If the paraboloid opened up and was cut by the plane, let's say z equals 4, then it would be whatever circle is cut by the plane, okay, as far as your region that you're setting over. Polar is going to make sense here, so let's convert this to polar. So we have double integral, square root of 1 plus 4r squared. dA then becomes r dr d theta. And we have the bounds from 0 to 2, 0 to 2 pi. Right, since we're going through this region in terms of polar coordinates. It is separable, so we can say integral from 0 to 2 pi of 1 d theta times the integral from 0 to 2 of r times the square root of 1 plus 4r squared dr. So we have theta evaluated from 0 to 2 pi. Here, underline 1 plus 4r squared. That would be our u in a u substitution. Derivative would be 8r, so 8 over 8, circle up. So we have times 1/8, and then 1 plus 4r squared to the 3 halves. So times 2/3. We need to evaluate that from 0 to 2. So this is going to be 2 pi times 1/12. And then if we plug in 2, so that would be 17 to the 3 halves, so 17 square root of 17. And then plug in 0, that's just 1 to the 3 halves, which is 1. So this is going to be pi over 6, 17 square root of 17 minus 1 as our surface area of this particular paraboloid over the given region above the xy plane. All right, find the area of the part of the cone, z equals square root of x squared plus y squared, inside the cylinder, r equals sine theta. So again, just to visualize what we're dealing with. So we have the cone, and this cylinder is a polar cylinder. So r equals sine theta, that's going to be this cylinder over here. Grab a different color. So essentially, we're looking for the part of, let's see if I can make that side a little bit more straight. So essentially, we are looking for the area of the cone inside of this cylinder. This cone is defined explicitly, so we can stick with the method we've been using. So the partial of z with respect to x is going to be x over square root of x squared plus y squared. Partial of z with respect to y is going to be y over square root of x squared plus y squared. It would be 2x over 2 times the square root of x squared plus y squared, but just in the interest of simplifying, this is what it would reduce to. So we could jump to our double integral over the region D, square root of 1 plus x over square root of x squared plus y squared squared plus y over square root of x squared plus y squared squared dA. So let's clean that up first. So double integral over the region D, square root of 1 plus x squared over x squared plus y squared over x squared plus y squared dA. So that's going to be double integral over the region D, So imagine this as x squared plus y squared over x squared plus y squared with a common denominator. It means we'd have the square root of 2 times x squared plus y squared over x squared plus y squared dA, which means we're just taking the double integral over the region D of square root of 2 dA. So this is going to be better in polar, so double integral in the xy plane, that's r equals sine theta. So polar makes sense here. Okay, so we have the integral from 0 to sine theta, 0 to pi of square root of 2 r dr d theta. So now let's integrate this. So we have, can't separate here because we have a bound in terms of theta. So 0 to pi of 1/2 r squared rad 2, 0 to sine theta d theta. So it's going to be equal to square root of 2 over 2, integral from 0 to pi of sine squared theta d theta, which requires a substitution with a trig identity. So that's going to be 1/2 minus cosine 2 theta over 2 d theta. Underline the 2 theta as a u, just to get that there. So that's going to be equal to the square root of 2 over 2 times theta over 2 minus sine 2 theta over 4 from 0 to pi. And that's going to be square root of 2 over 2 times pi over 2. So pi rad 2 over 4. As the surface area of the cone inside of that cylinder. One last example. Find the area of the sphere x squared plus y squared plus z squared equals a squared. That is outside the cylinder x squared plus y squared equals b squared, where a is greater than b. So really why I want to end with this is it's a good example where we can't parameterize in terms of spherical or theta and phi. If we try to parameterize a sphere in terms of theta and phi as we did earlier, it would be really difficult to determine the bounds of theta and phi that would be inside the cylinder. So in this case, we have to take a different approach to defining the sphere. So we can solve for z in terms of x and y. So z squared equals a squared minus x squared minus y squared. So then z equals plus or minus square root of a squared minus x squared minus y squared. Now, normally this presents an issue when we are parameterizing because we cannot parameterize with a plus or a minus. But what we're going to do to alleviate that issue is we're going to take the plus and say that the area is going to be symmetric above the xy plane and below the xy plane. So let's just focus on above the xy plane and double it. Okay, so we're just going to double the area above the xy plane. Okay, so now that it's defined directly, we can find those two partials. So partial of z with respect to x, that's going to be negative x over square root of a squared minus x squared minus y squared. Partial with respect to y is the negation of y over the square root of a squared minus x squared minus y squared. So then we can go to our double integral. We're doubling it over the region. Square root of 1 plus negative x over, just a lot of writing, a squared minus x squared minus y squared squared. I'm going to extend that out. And then negative y over square root of a squared minus x squared minus y squared squared dA. Now, I've done a bunch of the workout to save us a little bit of time and efficiency here. That's going to simplify to a squared over a squared minus x squared minus y squared dA. Now, the region that we're integrating over is outside the cylinder, inside the sphere. So that's really, if we draw two circles in the xy plane, we have radius b and we have radius a, so we're inside of this ring, so polar makes sense. So we're going to have 2 times the double integral from b to a, 0 to 2 pi, and we're also going to simplify this, so square root of a squared is a, and then a squared minus r squared to the negative 1/2 power, so I'll raise that up. dA becomes times r dr d theta. Now this is a typical u substitution integration. I'm confident that we'd be able to do it. It looks messy with the a's and the b's, but when all is said and done, we're going to get 2 pi a squared minus b squared to the 1/2. And that's going to be the surface area of the sphere outside the cylinder. But most importantly with this example is the fact that we cannot parameterize it in terms of spherical, because it would actually be more challenging than to take this more direct approach. So that's surface area. Next thing we're going to do is add functions into these integrals to define surface integrals. But before we get there, let's practice with the surface area, and I'll see you in the next video.